Hey guys, Mr. Riz here to help you out on the 223 part one. We're going to be looking at data transmission. So this first part is going to be a lot of like just information heavy for you. So we're going to take this quiz, kind of go through it together so you guys can understand some of the concepts behind here. So our goals here is to make sure we can explain data transmission using packets and protocols. We're also going to describe metadata and what information can be extracted from it. We're also going to try to use compound line prompts to explore how data is sent through the internet via packets using protocols and compression. And then at the end, we'll compare data compression algorithms to determine which is the best for a particular context. So when you guys are going to be using this here, make sure that you guys have some sort of image editing software. If you have like Microsoft Paint or Adobe Photoshop, that'd be great. So you might have to use a laptop, or you might have to just kind of Google some things. I'm sure there's like conversions here. Towards the end of the section, we're going to be converting data types or converting images to different types and seeing how the compression compares. All right, let's first talk about data transmission. So the internet is a computer network consisting of interconnected networks that use standardized or open, it's non-prioritized or there we go. We're going to try this again. We're going to use standard, basically open communication protocol. So there's nothing nobody has a claim over these things. So accessing items from the internet depends on the ability to connect to connecting a computer device to the internet connected device and the available bandwidth. So if we want to be able to get something from the internet, we got to make sure we have a device that can connect to it, and then we have something that allows us to get to it, and it all depends typically too on the bandwidth of the connection. So ever wonder how data is transmitted over the internet? So how do we just go through a website and just get that information? How do we take that information from another resource there and make it go through the networks and through the wires and into our device and onto our computer that we can look at and view and manipulate? All right, so can we think about some other examples how data is exchanged online? So what I want you guys to do is just think of different things like how can we get different types of data, like what information too can be exchanged online? Well, we can look at just text documents, we can look at coding, we can look at like HTML code for websites, we can stream videos like you guys are doing right now. What else can be done? Like so much, you can have open communication, so back and forth messaging between people. So a lot of different examples. We have so many different formats and they're all going through the same wires at the same time, but they all get put together differently when we receive at the end. All right. So for all this data to be exchanged, the internet to work, it needs to meet our needs. A lot of things got to happen behind the scenes. Luckily for users, that level of data is like abstracted. We don't have to worry about the ones and the zeros that are transmitting across the wires. In this activity, though, we're going to take a peek behind the curtain and we're going to learn about the core concepts behind the internet and the fundamentals of just data transmissions. So first, let's look at the networks and the internet. So computer systems are grouped of interconnected devices and programs that work together for a common purpose. All right, a computer network is a group of computing systems comprised of multiple interconnected devices able to send and receive information to each other. So you can see here we have an example of a computer network where we have some bigger computers and smaller computers, but they're all connected and we can weave them together. So this kind of, I always remember this like kind of back in the day, like when the original Xbox came out, we used to have like LAN parties. So we would all hook the Xboxes together through LAN connections. It wasn't any more complicated than just taking a bunch of wires and plugging them together. So each node in this diagram here represents a computer system that's connected to another computer system. So we got a computer here, computer here, computer here, computer here. Forming a computer network, these larger nodes designate larger systems capable of sending and receiving greater amounts of data, so they can send in more stuff than these smaller ones, even though the smaller ones still can, they just can't send as much. So you almost think about like cities or something like that. You have little towns and you have big towns. We want to go from one town to the other town. We could go through little towns, but it might be quicker to cut through some bigger towns that have more traffic. All right. So let's watch the following video here and then answer the questions below. Oh, and let me pull up that video for you guys.
day, whether for school, work, shopping, or entertainment. But do you ever wonder how the internet works? The notion of a network began to emerge back in the 1970s. Computers were connected to servers, which are large computers that host shared resources like files and printers. Groups of servers formed larger networks. These networks were mainly used by government agencies and universities. By the mid-1990s, networks had grown in size and number to become a global network of networks that make up the internet we know today. For the most part, these networks are physically connected by cables. It's hard to believe, but there are actually physical cables underground and along the ocean floor that connect servers across the globe. In addition to servers, many other types of computers are connected to the internet. Users, like you and me, who connect to the internet through a computer or a mobile device, are considered clients. We connect to the internet through an internet service provider or ISP, a service you pay for to have internet connectivity. So we all have these computers connected to the internet. How do they communicate? What happens when you click the send button or an email or type a website's address in a browser? Well, for starters, there are rules that define how data is exchanged over the internet. These rules are called protocols. Any computer must follow the protocols to be able to communicate with another computer on the internet. Since there are many different types of information on the internet, such as text, movies, and bank accounts, there are different protocols that handle the different types of information. One of the underlying protocols, called the Internet Protocol, or IP, dictates that every computer that's connected to the internet must have a numeric address, called an IP address, to uniquely identify it. Just like a postal address, IP addresses help computers find each other on the internet. So if a computer wants to send information to another computer, it needs the destination computer's IP address, just like you need your friend's postal address to mail them a package. Let's say Carla wants to email a picture to her friend Ben. She attaches the picture to the email and clicks send. Her computer needs to find out the IP address for Ben's mail server, the computer that manages email for Ben, which could be across town or a town in another country. IP addresses are made up of numbers in a specific format. For example, 104.20.78.237. But people have a hard time remembering all these numbers. So, IP addresses are given host name addresses that are easier for people to remember. For example, www.pltw.org. So, how are host names translated into IP addresses? Let's go back to our example. When Carla clicks send on her email, her computer sends a request to a domain name system server, or DNS server, asking for the IP address of Ben's mail server. DNS servers are like phone books. They maintain a list of all IP addresses and their host names they're associated with, like www.pltw.org or mail.myserver.com. After the DNS server responds with the IP address, Carla's computer sends the email to Ben's mail server IP address. Unlike a physical package that's delivered to your home, data that travels on a network is not delivered in one piece. It's broken into smaller pieces called packets, which are sent individually and put back together when they reach their destination. With millions of computers on the internet all over the world, packets need to find their way through a maze of computers to get to their final destination. For example, how would the packets from Carla's email know which computers to use to get to Ben's email server, which might be on the other side of the world? The answer is routers. Routers connect networks and control traffic on the internet. They decide which way the data packet should go to get to their destination in the fastest way possible. In some cases, packets may be sent to different routes to avoid network congestion or any potential routing problems at the time. For example, if a device malfunctions or a cable fails, data packets will be sent by a different route, avoiding a disruption in service. A system that can mitigate failures and continue to function is considered a fault-tolerant system. That's why the internet is so reliable. At any time, trillions of packets are being transmitted over the internet. It is the sophisticated algorithms that routers use that make the internet so fast and reliable.
Okay, so I have that video down here. I just have it in a slightly different spot. I'll move that up here after I get this done. So that video had a lot of information that we will slowly break down throughout this section here. So a network path can be moved or can be formed between any two devices on a network, creating a sequence of directly connected computer devices. So we got a picture of a network path. So we can see from the sender to the receiver here, just the path that can be created. All right, a network path begins with a sender device and ends at the receiver device, with a very number of devices in between. So we can have one, we can have two, we can have several hundred, but they're all devices. And the path doesn't always have to be the same way there. You think about how do you get to school? Typically, you might go the same way every single day, but some days you might go different routes depending on if there's a traffic jam or something like that. You can take different streets, you can turn on different roads, and you can still get the same location. You can still go from your house to school. As computer networks joined together to create larger and larger networks, the internet formed and grew to become a worldwide network. So since its inception, the network has grown exponentially. The first message was sent between UCLA and Stanford over the ARPANET in 1969. So 1 year later, by 1970, the network included a total of 13 computers. So pretty small, but you think about this was like what, 51 years ago, or 52. Basically, public use of the internet grew rapidly with the introduction of the World Wide Web in 1991 and the legalization of the e-commerce in 1995. So it was around, people could connect, but it wasn't until like the World Wide Web where people could get on the internet, check things out. And then in 1995, when people can start trading, e-commerce, that it actually started growing and being larger and larger. Today, the internet is involved in almost every facet of how we live, work, shop, learn. So you think about internet really wasn't that popular until like the mid 90s. So was that like almost less than 30 years ago, 25, 30 years ago? And now it's literally something, it's next to air and food that we need. Okay, so question for you guys, why were the networks created? Okay, so think about this here for a second, find the answer here. So the reason why networks were created were to share resources like files and printers. So the initial plan was to have everybody, transmit data. And it was a government project. They wanted to make sure they can send files from one place to another place and have it so that if one thing went down, it wouldn't just stop. So files were good resources. The other thing too is like printers. Before, if you had to have a printer that wasn't connected to a network, that means every computer would have to have a printer attached to it. Now that we have networks, we can have multiple computers attached to the same printer, and printers aren't used that too often. Okay, so next part, describe what each one of these network components do. So we got servers, clients, DNS, IP or ISPs, and routers. All right, so maybe go through here, start your own, and maybe pause this video here for a second, and we'll double check our answers. Okay, so a server is a large computer. Oh, I gotta zoom out a little bit here. Oh no. I'm sure I can get this all in here. All right, servers are large computers that host share files like files and printers. All right, so they're just a large computer that's able to share. You can both, like some schools have their servers. That's one thing I remember my dad was worked on them for banks. He just basically built servers for banks. They're super big computers that had a very tiny monitor. That's all I remember. All right, clients. Clients are the computers connected to the internet and that are used by consumers. So you think about like your home PC is a client, your phone is a client, your tablet is a client. So anything that's connected to the internet is a client. The DNS, these are like phone books. So they have a list of all the IP addresses built into them. So the way that you send things is you connect their IP addresses. So that like 4-digit or that 4-part code, 4-number code. That's how you go from one to the other. We don't ever see really what they are because like when you log into Canvas, you type in www.canvas.com. That's just a name that then gets associated through the DNS server to whatever IP address that is. We'll look at those things later. Your ISP is a service that you pay for your internet connectivity. So like I personally at home have, who do I have? Time Warner, which is like the worst thing ever, or Spectrum, that's what they're called. That's the only one I can get to, but that's the company that provides me the internet service. So they're basically the middleman to me to get onto the internet. And your router here is the device that connects to the network that controls the traffic of the internet. So your router, you have a wireless router. Most people, you have two of them, usually have a router that comes from the wall that connects to your cable, that your ISP provides. And that router sends information. Now, typically you have your router connected to a wireless router as well. So then you can work wirelessly, but that's what sends and receives messages back and forth. So we're looking at the components here. All right, next. All right, what is the internet protocol and what does it dictate here? So maybe pause this video and see if you can answer this question. All right, so the internet protocol is basically the underlying protocol of a network layer that is responsible for routing. So that's the protocol setup that we're going to use IP addresses to go through. And we just said right here, it dictates that every computer to the internet must have numerical address. All right, so basically, if we want to send and receive information, we've got to make sure that we're all sending the same type of information and we're all receiving it the same way. That way, if somebody sends something from one computer to another computer, and or vice versa, if we're connecting to a place far away, the information that gets sent to you is the same information that you want to receive. That way, there's no communication error. It's basically stating like everybody's going to use the same language, and this is how it's going to look like. The IP does not govern like what kind of information can be sent across the network. It just identifies like how the information will look. All right, so next question, how are data packets routed on the internet? Try to think back to the video and we'll answer this question here. Okay, so basically data packets are routed by routers from their source to their destination. So when we start, we send information through your router, right? Or you have your computer that connects to your router. And then from there, they must travel the same or different paths across the network traffic when they're available. So just like going home, like you're starting in your car, you can kind of think it's like your router. You put your packets, your information into it, and you take a pathway and it decides, or I guess maybe like a self-driving car would probably be better because it determines the quickest path to that spot. It might look to see like if there's, traffic along the way, it can reroute it to avoid. So basically, data packets are provided on the internet through the router. They're shared, split up to different connections, and they go to the path. Now, typically, there's always a two-way communication. We send something, then we hopefully get something back, but that's something we'll look at as well. All right, next, let's look specifically in those packets and protocols, and let's look at this video here. So we saw in the video that the data transmission over the internet is always broken into smaller chunks or packets. So when you send a file through the internet, if we have a big long movie, you're not getting that entire movie file all at once. You're going to break that movie up into small chunks and you're going to send them all individually. All right, to send to the destination using the fastest route possible and at the time of the data exchange. So it's always going to go the quickest route. Now, based on the traffic flow, it might go different routes. So packets carry data over the computer network using a defined set of rules called a protocol, which we kind of talked about before. This video here is going to answer a little bit more about the protocol. So let's watch that.
Hey, let's talk about packets and protocols. As we saw earlier in this activity, data transmitted on the internet is broken into smaller chunks called packets and sent to their destination using the fastest route at the time of the data exchange. We also talked about how communication on the internet has to conform to a set of rules called protocols, which work together to ensure that data is transmitted successfully from its source to its destination. At low levels of network abstraction, the on-off state of electricity is transmitted along a wire. At high levels of abstraction, you receive an email, access a web page, or stream music. And in between, it's all about protocols and packets. The Internet Protocol is the underlying packet structure for data exchange over a network and is referred to as the network layer. It is responsible for addressing and routing each data packet. The first rule of the Internet Protocol is that every computer connected to the Internet must be assigned a unique identifier called an IP address. Another rule of IP requires that all IP packets conform to a specific structure. Each IP packet must contain a header as well as data referred to as its payload. The header contains metadata, which is information about the packet itself that's needed for its transmission. This includes packet length, the source IP address, and destination IP address. The payload contains the actual data that's being sent, like the content of an email, a web page, or a video. The payload also contains information pertaining to other protocols used in the data exchange process. As the internet grew, the internet protocol changed over the years. Deployed in 1983, IP version 4, or IPv4, is still in wide use today. IPv4 uses a 32-bit address scheme, or 4 bytes that contain 8 bits each. This allows a storage capacity of 2 to the 32nd addresses, which equates to 4,294,967,296 unique IP addresses. That means IPv4 can provide just under 4.3 billion internet addresses. A common abstraction used to express an IPv4 address is the dot decimal notation. An IP address has 4 bytes. Each byte, or 8 bits of binary, is called an octet. Each octet in the IP address is converted to decimal. The 4 decimal numbers are separated by a period referred to as a dot. Dot decimal notation is much easier for humans to deal with than binary. Due to the phenomenal increase of devices accessing the internet over the last couple of decades, the 4.2 billion addresses were not enough and IPv4 ran out of addresses. The solution was that IPv6, originally released in 1994, began to be used to fulfill this increased demand. IPv6 uses a 128-bit address scheme, allowing for 2 to the 128th additional IP addresses. In place of the 4 octets of IPv4, an IPv6 address contains 8 groups of numbers, each containing 2 octets or 16 bits. Groups are separated by a colon instead of a dot to distinguish them from an IPv4 address. In addition to the internet protocol, the network layer includes routers that connect networks together and oversee the routing of IP packets across the internet. They use sophisticated algorithms to determine the fastest way to get them to their destination.
Okay, so let's take that information and see if we can answer these questions here. So what is metadata and where is it found in a packet? So think back to the video here for a second. Let's see if we can answer that. So metadata is basically the information about like who sent it, who's it going to, and how many packets that is going to be sent. So if you think about, if we're going to take a file that I'm going to send to you, we're going to chop it up into a lot of little pieces, but we need to have like a header to it that describes, okay, like what IP address is sending this, who is going to receive this, and then how many times did I chop it up? So how many packets should this be received? And I guess this should also be what number packet is this? So is this packet 1 of 35 or is this packet 4 of 22? And so we can get through. So if you're going to get a packet, you're sending a packet to somebody, you chop it up into 56 different pieces. They're going to go ahead, and because it takes different routes, you might get packet 2 before you get packet 1, or packet 7 before you get packet 3, but you're going to get them all together, and then you're going to get those pieces, put them together like a jigsaw. There's your complete packet. So your metadata sense tells who it was from, who's it supposed to go to, the packet number it is, and how many packets total you'll earn in the beginning. So here we go. What are some examples here? We got the source IP, the destination IP, and then even the packet length, how many packets it is. All right, what does a packet payload contain? So the packet payload is actually the ones and zeros that are like built inside. So it's your little pixels of your images that get sent over, or the information in your HTML code that's being sent over. So the packet payload contains let's see, does it contain the actual data that's being transported? Yeah, it does. Does it contain the source? No, the packet payload doesn't tell us where the source is. That's the metadata. The packet contains the data type. No, that's the metadata. It tells us what kind of data it is, and the metadata information. Yeah, all this is kind of the same thing. The packet payload is actually the information being sent over. So what's the difference between IPv4 and IPv6? Well, the IP address is made out of 4 bits. That's IPv4 because there's 4 bits. So there's 4 bytes, 32 bits. The one with 16 bytes would IPv6. All right, and you can see there's a big difference between how they look, and later on in another activity, we'll look at your IP address, comparing the IPv4 to the IPv6. I don't get why they call it IPv6 when they're 16 now, but it's kind of easy. All right, so how many IPv6 are possible? So there is 2 to the 32 power. So let's look that up real quick because I'm lazy. It does want us to type that in. So there is, copy paste this over here, 2 to the 32. There is 4,294,967,296 IPv4 addresses possible. How many times larger is IPv6 compared to IPv4? Well, we know that there are 2 to the 128 power IPv6. If we divide that number by 2 to the 32 power, what we have to do here is when we're dividing, we subtract exponents. And so 128 minus 32 would be 2 to the 96 power more IPv6. So can we even type that in Google? 2 to the 96 power. Oh, it doesn't even pop up there. Let's see if does anybody have one here. I could make a Python program real quick. All right, there we go. Somebody did it. So we would have to fill up, it took us a couple years to fill it. There's like over 4 billion IPv4. We would have to fill those up that many number of times. Geez, how many? 100,000, millions, billions, trillions, quadrillions, quintillions, sextillions, septillions, over almost 8 octillion times before we run out of IPv6. So I think we got a while, but it's still unlimited because every new device becomes a new IPv6 address. Okay, we got one more video to watch and a couple more questions to answer. So let's watch this next video.
So we've seen how the Internet Protocol takes care of the addressing and routing of data packets. But how does each individual packet know what to do when it reaches its destination? The coordination of data transfer requires a lot more detail than addressing and routing. For example, which software application on the receiving machine should accept these packets? What if there were some errors in the data transfer? This is handled by the transport layer. One of the most common protocols at this layer is the Transmission Control Protocol, or TCP. TCP sits on top of the IP layer, so it's referred to as TCP/IP. In other words, a TCP packet resides inside the payload of an IP packet. Like IP packets, a TCP packet has a header and a payload. The metadata in the TCP header includes fields like sequence number, port numbers, and some error handling data. When the packets arrive at their destination computer, TCP uses the sequence numbers to assemble the data packets in the correct order. Then, TCP uses the destination port number to deliver the packets to the correct software application. TCP is a very reliable transport protocol because before it sends any data, it ensures that a connection is established between the source and destination. This is called a TCP handshake. It requests that any missing packets be resent to ensure no data packets were lost during the transfer. And it also resolves any duplicate packets. Because of its reliability, TCP is used with applications that don't tolerate any loss of data. Imagine receiving an email with some missing words or phrases, or a document with a missing paragraph. This is why applications like a web browser, email, and file transfer use TCP. The last protocol we will discuss is the User Datagram Protocol, or UDP. Like TCP, UDP sits on the IP layer and is sometimes referred to as UDP/IP. As an alternative to TCP, UDP is used for sending data over the internet at a much faster rate, but at the price of possible data loss and no handshake. This means that the receiving end may not be ready for the data. Unlike TCP, UDP does not check for missing packets, nor does it reassemble packets as they arrive. It receives and forwards packets to the application port without any extra verification. This makes UDP much faster than TCP and a great fit for applications that can tolerate dropped packets without much impact on the quality of the connection. So what if a few pixels are dropped in a video? It's not the end of the world.
Okay, so now that we know basically through the IP header, like what packet we have and going through, we're going to look inside the packet payload itself. And we determine like what kind of information this is. Like, is this a video that we're streaming? Is this a document that we're sharing? Is this a website that we're viewing? And in that information here, we're going to determine whether we should exchange that through a TCP or a UDP. So once again, it's almost like a protocol inside of a protocol. And so we'll look at the difference between the 2 points, but the main job of the transport layer, so inside the payload, is to determine the type of information that we're using and the type of handshake we should establish. Should we establish a secure handshake to make sure that none of the packets get missed out and none of the data is lost and we have a full transfer of data? Or should we establish a quicker handshake so we can send data quicker and faster using like the UDP? So what's the difference between the two transfer layers here? The TCP is more reliable because it establishes a connection between the two. So before any information go through, you have a good handshake and you're confirming that you're going back and forth. Basically, there's a small amount of data that gets sent back and forth to establish the connection between the two. The UDP is less reliable, but it makes the connection faster. So you can think about like different informations here that we want it. Like a TCP, if we're going to send information, like if I want to get a document from you, I want a TCP because I don't want any part of that document missing. Now, if I'm going to be trying to stream a video or listen to a podcast or something like that, I would probably want a UDP. It doesn't matter, you know, especially if I'm on my phone or anything like that. If I'm missing a little bit of data, it doesn't matter. You think about too, a lot of cell phones use UDP because if you look at like different types of browsers, there's like a mobile version and a regular static version. The mobile version might be a UDP handshake because that way, you know, if a little bit of the information, if one image doesn't load up completely on the website, it's going to load up a lot faster on your phone than it would be if we had to sit there and wait for a complete connected, established connection. All right, so what kind of data is inside the UDP metadata? Well, the source port and the destination port. So basically saying like, where is this going to go to? Like, is this going to go to not just the computer, but like, is this going to go to a web browser or is this going to open up an audio file or something like that? The sequence number and the packet payload. Think about it here for a second. No, not the packet payload. So remember, this is the TCP and UDP is like a metadata inside of the kind of packet payload itself. So the packet payload is still the information being sent. It's the image files, the image pixels. But this stuff here is inside. After the IP handler, IP protocol, we just have the port and the destination port and the sequence number. All right, so let's take a look at this quiz. How did we do? I have a couple that are left blank. I'm gonna see if I kind of messed up my answer key at all. 3 out of 5. Okay, ooh, I messed. Oh, that one has to be hand graded. And that one was good. That one was good. That one has to be hand graded, and that one has to be hand graded. And all right, so if you watch this, you should be doing all right here. Okay, so let me tell you guys what you guys are going to work on next for part 2. Kind of splitting this up here just because I know I probably will be out during this time, and hopefully you guys are just watching this video and following along. For part 2 of 3, you guys will take a quiz here. So a quiz over the same information that we just went over. It's just going to be more of a grading quiz. So you guys have 2 attempts to take this quiz. Feel free to work together on these. You know, if you want to take this with somebody in the classroom at the same time, you guys can compare your answers. If you're not sure, maybe you guys can on your first guess work together and be like, all right, I guess true on this one, you guess false, and we'll put our answers together, see what it is. But hopefully it isn't too bad and you guys can answer these. Use some logic too. So that's part 1 and part 2, guys. I will see you guys again for part 3. Have a great one.